Hello there! Welcome to Students of Mathematics on YouTube. This is your teacher online, Teacher Romelinda de Guzman. Today, we're going to learn a very important topic in math called simplifying radicals. And we limit our lesson with the radicals of the same index. I know that this is one of your most hated topics. Please give me the chance to show you the beautiful and very easy ways to study this concept. They may look very difficult to comprehend, but I assure you, you will find them very interesting. So why not join me navigate the world of the square root, the cube root, the fourth root, and the fifth root. Let's have a review. In the previous lesson you learned a raised to 1 over n is defined as the principal nth root of a. In radical symbol, we have the nth root of a, which is equivalent to that previous expression a raised to 1 over n. And for a is greater than 0 and positive integers m and n, where n is greater than 1, a raised to m over n is equal to the nth root of a raised to m. So this is just transforming an expression with fractional exponents to radical form. So you are already well versed with that. Now let us further study radicals. And the first that we're going to tackle for this time is we have the laws of radicals. The first law is the nth root of a raised to n is equal to a. Because when we are going to transform this particular expression into the exponential form, we have a raised to n over n, wherein the exponent is a fraction that can be reduced into 1. That's why this particular law of radical is equal to a. Or simply, when we're going to study further, if they have the same index with the exponent of the radicand, then we can just cancel the exponent and the index. And there you go, we have the simplest form of it. For letter B, or the second law of radical, we have the nth root of a times the nth root of b is equal to the nth root of the product of AB. Very easy and very simple. Just like when we have the square root of 3 times the square root of 2 is simply equal to the square root of 6. For letter C, we have the nth root of the fraction a over b can be written in a simplest or simpler form as the nth root of a times the nth root of b. And then for further study of this one, we can simplify further later on. For letter D, or the last law of radicals, we have the nth root of the nth root of a. So this is a double radical. Take note that there are two radicals with the same radicand. So we have the mnth root of a, or we're going to multiply the radical, or the index I should say, in order to come up with a simpler form of the radical. If we take a particular example of this one, we have, if you have the cube root of a, the cube root of, wait, let's have, if you have the cube root of the square root of a is equal to the sixth root of a, because the index of a in the radicand is 2. That's why when you multiply 2 and 3, you come up with 6. That's how it is for the fourth law of the radical. And now we can come up with some particular examples on the first law. For example, if you have first law, we have the fifth root of, wait, that's not how it is written. We have the fifth root of x to the fifth power, so it can be simply written as x. If you have the cube root of 2 cube, it can be simply written as 2. For the second law of exponent, you have, if you have the cube root of 9 times the cube root of 3, you can have the cube root of 27. As simple as that one. For letter C, if you have the square root of 5 over 4, we can simply rewrite that as the square root of 5 over the square root of 4. Take note, we are just applying the laws of the radicals here. We are not yet simplifying the radicals. For letter D, or the last of the laws of radicals, if you have the fifth root of the cube root of 5, we can have it as the 15th root of 5. Did you get that? So we just multiplied 5 and 3 to come up with 15, and we retain that radicand 5. Okay, so I hope you don't have any concern that was not addressed in here. So let's proceed to the next one. We are now on how to simplify radicals with the same index, which is our main lesson for this time. There are 3 ways on simplifying radicals. The first one is removing the perfect nth powers from a radicand, which we will have an example later on. The second one is reducing the index of the radical to the lowest possible order, or we call it into the lowest possible index. And then for the third one, we have rationalizing the denominator of the radicand. So in here, we come up with the first one. This is removing perfect nth powers of the radicand. So we take note of the nth power. And so for this particular example, this is a square root. That's why we apply, there is a 2 in here, but if it is a square root, we usually don't write it. So this one is, since it is a perfect square root, because the radicand is a perfect square, then we can just have or cancel that one with the radical, so the answer is 5. Okay. For the second example, this is the first example. For the second example, we have we will apply here the second law of radical, because we can see that we have square root of 4 times the square root of y to the 6. This is applying the nth root of a times the nth root of b is equal to the nth root of ab. So in here, 4y squared is already a product ab. That's why we tried to break them down into this form. That's why we individually take note or simplify. This is, we know that the square root of 4 is 2, but let's try to have it, express it in the exponential form 2 squared. And then the square root of y to the 6 can be broken down into the square root of y squared, then another square root of y squared, then another square root of y squared. Can you follow? Because when we're going to multiply this and this and this, we come up with y to the 6. Remember the laws of exponent. When we multiply numbers with the same base, we add the exponent. So that's how it is broken. Now, so we cancel that one because we remove the perfect nth powers. So we have 2. Then we cancel also the exponents in this expression. So we have, for this one, we have y times y times y. Then when we're going to simplify or multiply these numbers, as we have extracted them from the perfect nth powers or the square root, so we have the final answer is 2y cubed. Can you guess why is it computed as y cubed? Because we have here 1, another 1 in there, and another 1 in there. And then when we are going to add the exponent, so the final answer is this one. Okay, I hope you can follow. The next, we can have the next example. We have the fifth root of 64. So this time we again recall what we have. We know that when it is fifth root, we are going to think of the factors of 64 so that one of the factors is a perfect fifth or is a number that is expressed to the fifth power when it is an exponent. So we know that we can have it as 32 and 2. And then applying the second law of radicals, we have the fifth root of 32 times the fifth root of 2. Then this 32 can be expressed in exponential form as 2 to the fifth power. Can you check on that? We have 2 times 2 times 2 times 2 times 2 gives you 32. That's already 2 multiplied by itself 5 times. And then the other factor is retained as is. That's why this would cancel. So we have 2 the fifth root of 2. That's how to write the answer. So this is already a whole number. It's no longer inside the radical because it's a perfect fifth power, and then this one remains inside the radical sign because it's not anymore perfect and it's already the simplest form. For the I think this is the third example for reduced or removing perfect nth power from a radicand. This is the fourth example. For the fourth example, you can see that okay, this one should be extended up there. So it is read as the fifth root of 3 to the fifth, x to the sixth, y to the third power. So take note, we're going to break them down so that we can come up with simplifying them. The fifth root of 3 to the fifth, that's the first factor. Then we have the fifth root of x to the sixth, and then the fifth root of y cubed. Take note that for the first one, we can cancel that. So it's just be 3. For the other one, there is still a perfect fifth power inside the radical sign. So we can break it further as the fifth root of x to the fifth times the fifth root of x. Okay, so that when we verify, we have x to the fifth times x to the first power gives you x to the sixth. And then for the other factor, let's not forget to include still the fifth root of y cubed. So this is again 3 times, we will cancel that, so this is x. And then this one is, take note, this one is already the simplest form, and also this one. That's why we have to rewrite that as expressions inside the radical. So we have the fifth root of x y cubed. Alright, so the final answer we have 3x fifth root of x y cubed. That's how to remove the perfect nth powers from a radical. So the perfect nth powers, we have 3x, 2x here. And then those that are not anymore perfect, like this one, they have to stay inside the radical sign. And we must also know how to read them as, for this one, we have 2, the fifth root of 2. This one is 3x, the fifth root of xy cubed. Let's move on. For letter B, or the next way on simplifying radicals, we have reducing the index of the radical to the lowest possible order. So we have this particular example. The first one is read as the sixth root of 4 to the third power. Now, we can go back to your previous lesson of simplifying this, and we are going to rewrite this into the exponential form. So it should be 4 raised to 3 over 6. This 3 over 6 can be, of course, reduced into 4 raised to 1/2, correct? That's why when we are going to rewrite this one into the radical form, we come up with the square root of 4. That is the exponent 1, which is that one, and then the index is 2. Okay, but we don't write the index 2 when it is square root. Alright, so of course we can still further simplify that using simplifying radicals step number 1, removing the perfect nth power. That's why we have the square root of 2 squared, which is equal to 4. That is this 2 squared is equal to 4. That's why we can cancel that 2 with the index, so the answer is 2, or the square root of 4 is 2, like that. For the second example, we have the 8th root of y to the 6th power. Again, we do the same as how we did that in number 1. So we have y raised to 6 over 8. That can be reduced as 3 over 4. So what will be the index? The index for the new radical with the reduced, or that is expressed in the lowest possible order or index, is the 4th root of y cubed. And since this exponent in the radicand is already smaller than the index, you can no longer simplify. Take note of that. For if there is an exponent in the radical, but it is already smaller or less than the indicated index, then it is already in the simplest form. Otherwise, if this index is smaller and the exponent inside the radical sign is still bigger, then it is still to be simplified by applying step number 1, removing the perfect nth powers from a radical. Next, let's have another one. We have rationalizing the denominator of the radicand. This is already the third. This is already the third in simplifying radicals, or third way in simplifying radicals. So, take note that when we have a fraction as a radicand, just like 1/2 and 2x over 3y, these are not in the simplest form because they are fractions. So the first thing that we're going to do is, just like how we did that in the laws of radical letter C, we are going to rewrite it as square root of 1 over square root of 2. For the other one in here, we have square root of 2x over square root of 3y. But we have here the term rationalizing the denominator. We have already applied the third law of radical, wherein we have removed the fraction inside the radical sign by doing it this way. But it is not yet, or thus that is not the end of simplifying it, because any number or any radicand in the denominator is not yet in the simplest form. So we should still simplify further an expression when there is still a radical inside or at the denominator. So that is how we do. Rationalizing is the process of removing the radical sign in the denominator. Of course, we just don't remove it so that it will become square root of 1 over 2, or it will just become 1/2, because square root of 1 is 1. But what we do here is we are going to do some more computation, but it is not that difficult, not as difficult as what you think. So how to rationalize? We are going to think, may I just write it here, square root of 1 over square root of 2. We're going to think of a number that can be multiplied to 2 so that it will become a perfect square. And of course, there are so many numbers that can be multiplied in here, but we have to multiply the simplest, or we're going to come up with the simplest one. Of course, the simplest one is square root of 2. So what we multiply in the denominator should also be multiplied in the numerator, so that we are not changing the value, because it looks like we have just multiplied 1, because square root of 2 over square root of 2 is equivalent to 1, right? Alright, so now we do some kind of multiplication, the one we learned in laws of radical B. That's why we have square root of 2. Square root of 1 times square root of 2 is square root of 2, then square root of 4. And of course, square root of 4 is a perfect is a perfect square, or 4 is a perfect square. That's why we can remove the perfect nth power from a radicand in the denominator, and we come up with an answer which is already like this. It is read as a square root of 2 over 2. It's already in the simplest form. And we have successfully removed the radical sign in the denominator. Take note, this is just to remove. Rationalizing the denominator is removing the radical sign in the denominator in such a way that we are not changing the value. Now, pay particular extra or pay attention to this answer. Your answer is square root of 2 over 2. Take note, we cannot cancel 2 here and 2 here because they do not have the same value. If we take the value of square root of 2 in the calculator, it is not the same as 2. That's why they cannot be cancelled. 1 is under the radical sign. It has still to undergo some operation to come up with the actual value, and the other one, 2, is already its actual value. That's why. So that's it. Wait, so again, we have square root of 2 over 2. For the next one, we have, of course, we also answer, or we also try to answer number 2. This is example number 1. This is example number 2. For number 2, so we have rewritten it as square root of 2x over square root of 3y. Now, we are going to rationalize the denominator. Whatever it is in the denominator, in the numerator, there's no problem with that. For as long as it's already in the simplest form, using simplifying radicals letter A and letter B, removing perfect nth powers from a radical, and reducing the index, no problem with numerator. But what we're going to remedy is the denominator. We do not like a radical sign in the denominator. That's why we have to remove this radical sign. So think again of a number or an expression that can be multiplied to 3y so that it will become a perfect square. So the answer is, what are we going to multiply? We're going to multiply here square root of 3y, correct? Over square root of 3y. So that the result will be square root of 6xy in the numerator. Take note of that. We will multiply 2 and 3 and then x and y, like that. So we come up with 6xy over the square root of 9y squared. And of course, if we simplify this denominator using a and b, removing the perfect nth power, we have, and reducing the index into the lowest possible order, we come up with square root of 6xy over 3y. Square root of 9 is 3. Square root of y squared is y. So that is already the final answer. Take note again that we cannot cancel. In no way we can cancel 6 and 3 or reduce it into 2 because they are not in the same order. One is in this inside the radical sign and the other is already a plain number, or the actual value is 3 already. Okay, let's move on to the next example. We have the fifth root, the square root of 5 over x cubed. Again, this is not in the simplest form. It's because it is a fraction, right? That's why the first that we're going to do is to rewrite it in a simpler form, like that. But then again, we have in the denominator a radical sign. That's why we have to rationalize the denominator. The term that we are doing here is we are going to rationalize the denominator or remove the radical sign. So removing it, we're going to multiply it with the lowest number or expression so that it will become a perfect square. Now, tell me the reason why it is x. It's because when we multiply, we have the fifth or the square root of 5x in the numerator over the square root of x to the fourth power. And this expression x to the fourth power is a perfect root of, there's a perfect root of that if it is a square root. Okay, it's a perfect square number. Alright, so how? We again apply removing the perfect nth power and reducing the index into the lowest possible order. So we have square root of 5x over, take note of this one, if you're going to compute, we have x raised to 4 over 2 or equivalent to x to the second power. That's why you have x to the second power. You cannot again cancel this x here with this x here because they do not have, they are not to be cancelled, they are not the same in value. One is under the square root sign and the other one is the actual value already of x. Okay, that is rationalizing the denominator. Another one we have, this is, I think this is the fourth example or fifth maybe, whatever, for as long as we learn how. Okay, again, this is a fraction, so again, it's a square root of 5 over square root of 2x cubed. What makes it different with the previous example? We have 2 here. So what are we going to multiply so that it will become a perfect square and we can rationalize the denominator? Of course, if we have multiplied a while ago the expression without the 2 with square root of x, then because it has already 2, what makes it a perfect square number? We have to multiply another 2. So what we have as a number to rationalize the denominator, we can use that as a number to rationalize or to multiply it in the numerator so that we will not be changing the value of the expression. So the final answer will be the square root of, right, 10x over 4 square root of 4x to the fourth. And take note, this is already a perfect square number, this 4x to the fourth. That's why your answer will be square root of 10x over 2x squared. Okay. Okay, let's try cube root this time. So again, we're going to have, or to rewrite it into separate from the numerator and the denominator. We have cube root of 5 over the cube root of 4. So again, our goal is to rationalize the denominator. We're going to think of a perfect number that can be extracted into its cube root. So we're going to multiply, or we're going to come up with a number that is to be multiplied to 4 in order to become a perfect cube. That's why we have to multiply it with the cube root of 2, and that is also to be multiplied to the numerator. So applying laws of radical number 2, we have the cube root of 10, right, over the cube root of 8, because 4 times 2 is equal to 8. Then, simplifying further, we have the cube root of 10. We can no longer simplify that one because there's no factor of 10 that is a perfect cube. But the cube root of 8 is 2. That's why we have this final answer as the simplified form of the cube root of 5 over 4 is equal to the cube root of 10 over 2. And it is in this one is simpler than this one. Okay, I hope you have no more questions on simplifying radicals with removing the perfect nth power, reducing the index to the lowest possible order, and rationalizing the denominator. But still, I have one more concept to show you this time. This is a bonus one. Some in other books, this was not included, but I would like you to learn this one. Okay, how are we going to simplify an expression like this? 5 over the square root of x minus 3. Take note that the square root of x is not in negative 3 there is not included. So 3 is subtracted from the square root of x. That's the meaning of that one. So in here, I would like you to take note one important word, and that is what we call the conjugate. Okay, we are in order to rationalize the denominator, we are going to multiply the denominator and the numerator with its conjugate of the denominator, and the conjugate is the square root of x plus 3. That is to be multiplied in the numerator and in the denominator, the square root of x plus 3. Take note, the conjugate is just, we just change this negative sign into the positive so that it will become a conjugate. That's the simplest way on how to explain that. Of course, we apply still multiplication in here, so we multiply 5 to square root of x, and we also multiply 5 to positive 3. The result will be 5 the square root of x plus 15 over, guess what? How are we going to simplify the denominator? Okay, let us not forget the FOIL method. So first terms, square root of x squared, correct? Then we have outer terms. We have positive 3 square root of x. Then we have inner terms, negative 3 square root of x. Last terms, we have negative 9. If we're going to inspect, this positive 3 square root of x is cancelled with negative 3 square root of x. And then take note, x squared in the denominator is already square root of x squared, I should say, can be reduced into x. So if you're going to inspect the whole denominator, you will notice that the radical sign is already eliminated. That's why it can be rewritten further as 5 square root of x plus 15. Take note, you cannot combine 5 and 15 in here. Over, you have x minus 9. Alright, so that is already the answer. We have already removed the radical in the denominator. How? By multiplying the denominator with its conjugate. Let's try to see another example for that particular for a particular example that is closely related to this example so that you can compare. Okay, for example, you have 5 over the square root of x plus 3. What do you think will be its conjugate? The conjugate will be the number square root of x minus 3 over, we have square root of x minus 3. So the conjugate is to be expressed as a whole number, square root of x, expressed as 1, square root of x minus 3 over square root of x minus 3. So again, we multiply using how, let's do what we did in the previous example. So we have 5 square root of x minus 15 over, again, can we do that once more? We have square root of x squared. That's first terms. Outer terms minus 3 square root of x. Inner terms plus 3 square root of x. That's 1. Okay, minus 9. The answer is 5 square root of x minus 15 in the numerator over, this becomes x. That would cancel, so the answer is x minus 9. So this is already the final answer. Wait, okay, may I just write it in here? So we have x minus 9 because these two at the middle, the two middle terms are cancelled. So there you go, my dear students in mathematics. We're done with simple lectures on simplifying radicals, and we have learned how by removing the perfect nth power, by reducing the index to its lowest possible order, by rationalizing the denominator. And in rationalizing the denominator, we also learn another term. We multiply it with its conjugate. We multiply the denominator by its conjugate. There are a lot more that we can learn in simplifying radicals because our topic is only simplifying radicals with the same index. For the next one, for simplifying radicals, operation and radicals, continue subscribing us on YouTube. And for now, it's have a nice day. And in closing, we have this quotation: there's nothing too difficult to conquer if we put our heart into it, and God will crown our efforts with success. That is paraphrase from the Holy Bible, and I hope you can gather so much joy in pondering on this one. Happy learning ahead.